rural
Just to
area in
let
the
you know, I'm
mountains,
pressing
so.
the live button.
Okay.
So now everything you say is live to the audience. Yeah, no, we've got like 2% of Canada vaccinated now, so it's going slow, but
Yeah, there was a story in the paper recently about that couple that flew up from Vancouver
yeah. That's an
to get their
embarrassment
shots,
to my province.
and he lost his job too over it.
They flew to the Yukon
Yeah.
to get their vaccinations, and yeah, people were not pleased, and they're like multimillionaires. So they took a private jet, flew to the Yukon, got in a First Nations community. Like it's the worst of the worst. Yeah.
Yeah, it couldn't look any worse if you tried.
No. Those people need to get unvaccinated. I'm not sure how that would work. Someone could just like pull all the vaccine back out. But
Oh, Twitter was alive with all kinds of suggestions, you can imagine.
yeah, I'm sure. Yeah. It is, and I've heard now that with some of the variants, they might be thinking about maybe we need 3 shots now
Really?
instead
Wow.
of 2 with some like the South African variant and the Brazilian variant. Yeah, but they do still work. So yeah, this will end. We're gonna get back to normal time. Everything's
Yes.
gonna be fine. Yeah, and we'll all meet in person. That's what'll happen. I'm gonna say hi to people. I always forget. Hello to 6 Bob Ohms, Andrew Planet, Astro B, Bob Moeller, David Dunn, David Fairweather, Horizon Brave, John Seinfeld, Johnny J, Luke Duke, Martin Bradshaw, Nancy Graziano, Nif T, Rich Wilson, Arjone, and Zaffin. Hey, everybody. Just a reminder, I'm going to be interviewing... I got to grab the book with my foot. So I'm going to be interviewing David Brown tomorrow about the mission. And I won't read the subtitle because it just goes on forever. But the gist is it's the trials and tribulations of the Europa Clipper. And it's terrific. He's a fantastic writer. Just so funny. And it's kind of interesting because I know the players now. So there's a whole section talking about Alan Stern and whole sections talking about different people, Carolyn Porco, all people involved on the various outer planets projects and just what it took. And also goes into a lot about GEMO. Remember the Jupiter Icy Moons Orbiter spacecraft? Oh, that's like the saddest thing ever. But then in retrospect, when you think about what's happened with James Webb, it kind of makes sense that to cancel a giant Battlestar Galactica type, what was it, a nuclear powered, a fission reactor powering an enormous number of ion engines so that it could fly to each of the icy Galilean moons, one after the other, orbit them, deliver landers, and just do all kinds of crazy stuff. Yeah, no, actually, now that I'm saying these words out loud, it just sounds like it just would have been a disaster.
Or a great dream.
Yeah. But I always sort of go back to the missions that I really wish had flown, and GEMO's one of them. The Terrestrial Planet Finder is the other one. But then again, right? 4, 6 space telescopes flying in formation, doing interferometry in space. Yeah, maybe that's a step too far. So, okay. Well, I think we've reached the 5-minute mark, so why don't we get this started? All right, I'll put you guys. So, apologies. We don't have the little ribbon that shows the people, and I have to figure that out. So I will. I promise. Speaker view. There's me. And here we go. Hello and welcome to the weekly Space Hangout for Wednesday, January 27th, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about messaging the cosmos, the universe in formation, and everything to see in the night sky. Joining me this week on my screen right now, I got Carolyn Peterson. Hey, Carolyn, space writer.
Yes.
And in space, you got to show the cat.
Oh, yeah. Here you go.
Yeah.
For all the cat lovers in the audience.
But I was mentioning this before the show, that it feels to me like that you are on New Shepard. You're at the sort of the high part of the flight, or maybe you're on the Virgin Galactic. You've reached the top part of the apogee of your flight, and now you are, and yet the cat is probably hanging on for dear life so that it doesn't float around the cockpit. As they would be, yes. Yeah, as they would be, yeah.
Yeah.
Right? You've got a cat that is sitting there on the windowsill while you're in orbit. I've seen enough of the Expanse now to know what happens when people are in orbit.
It's the future.
We've got Pam Hoffman. Hey, Pam. Welcome back.
Thank you, Fraser.
And we've got, I like the background, by the way, Pam. That's really cool. Yeah, all of the constellations. Are all 88 constellations on that wall, or did you?
I don't even think it's for real. It's just a graphic.
I see the Dipper. I see the Big Dipper right there behind you.
Probably repeated several times.
Oh, okay. Several Big Dippers. Okay, wait a minute. I think I see Gemini over there, above your shoulder. All right. Well, I won't push your constellation knowledge anymore. And we've got Chris Carr. Hey, Chris. Welcome back.
Hi, Fraser. Glad to be back.
Man, everyone's got different camera setups here. I'm sort of shifting to try and average out here. I'm trying to normalize the real estate. Okay. All right. We're good. Now, before we get into our special guest this week, I just want to give, of course, a huge shout out to our good friends and executive producers at the Weekly Space Hangout crew. They are, of course, our friends, really our family that manage the show. They produce the show. They choose all the guests. And we couldn't do this without them. So if you want to be a part of this amazing community, go to wshcrew.space. They will hook you up, give you your executive producer privileges, and put you to work, bringing on new guests for the show, as well as giving you places to hang out and chat with other space fans. All right, let's get on with this week's guest. So this week, we're joined by Dr. Marie Cody. Dr. Cody, welcome to the Weekly Space Hangout.
Thank you. It's a pleasure to be here.
So the question I always ask people, who are you? What do you do?
Well, I wear a number of different hats, but I think the one that your audience is most interested in is that I am an astronomer at the SETI Institute in Mountain View, California. And for the past decade or so, I've been working with space telescopes and specifically looking at the brightness fluctuations of thousands of stars across the sky. For various research purposes, which I'm happy to talk about.
Yeah, well, let's get right into that. So, but you're part of the SETI Institute, so you know there's a certain flavor to the kinds of work that the SETI Institute likes to work on.
There is, and I should say I'm relatively new at the SETI Institute. I also have been working at NASA Ames Research Center. And primarily studying the youngest stars. But I moved over to SETI more recently and have gotten very interested in thinking about how we might detect life and other civilizations associated with faraway stars in our galaxy.
So let's spend some time first talking about just the traditional science before we engage in Fraser's flights of fancy. What work have you been doing in measuring star brightness?
Yeah, so NASA and in fact also the European Space Agency has had a series of space telescope missions over basically the past decade. You may be familiar with the Kepler telescope, which isn't operating anymore, but it was up there sending us wonderful data for about almost a decade. And now the NASA's TESS mission is flying. And basically what all these space telescopes do is they have a huge field of view on the sky. And they look at hundreds of thousands of stars at the same time, just taking image after image. And they send those down to us astronomers, or really actually anyone in the world can analyze the data. That's kind of a fun thing to know. And we take those images and through some analysis manipulation, we measure the brightness associated with each of those stars, or whatever subset you're interested in, and you get the light curve of the star, the brightness over time. And the chief reason most of these missions were funded by NASA was to look for exoplanets, because if you have an exoplanet in transit, when the exoplanet passes in front of its host star, as many folks may know, it blocks off the light and you get a little dip in the light curve. And these space telescopes make very high precision measurements, which enable them to find very small, potentially Earth-sized planets. And that's something that Kepler is very good at. Now TESS is doing. But we can do a whole lot of other science looking at the brightness of stars that may or may not have planets.
That's interesting. And using the same telescope, using TESS, using Kepler, looking for star brightness, but looking for other phenomena than just, is there a planet there?
Exactly. Yeah, and that's been done obviously for many years by professional and amateur astronomers alike. There are pulsating stars. People may be familiar with, Cepheids and or Lyra stars. Some of these are used to measure distances.
Yeah, it's kind of how we know the universe is expanding.
Yeah, exactly. But the thing is, some of these stars, and particularly the young stars that I've been studying for a while, they have a lot of complex behavior on a wide variety of timescales. And when you use a telescope from the ground, you don't get all the information you need, because you get daytime coming when the sun comes up. You
Right.
get bad weather. You have to share the telescope with other astronomers.
Man, the three things that astronomers hate, right? The sun, clouds, and sharing.
Yeah, exactly. So what's really changed, in addition to the very exquisite precision of the measurements from space, you don't have to look through the atmosphere, so you don't get these fluctuations in basically stars twinkle when you look at them through the atmosphere, and so you can't measure their brightness very well, or at least below a certain threshold. But the big thing that's changed is that Kepler and now TESS will stare at stars for a couple months straight, and you get this uninterrupted data stream where you can see what these stars are doing in their full complexity. So you're no longer missing out. So of course, for the exoplanet hunters, it means they don't miss the transits of planets. But for folks like me who are studying more complex behavior, some of it's random, some of it does have interesting patterns to it, but we couldn't see it or fully appreciate it before. We now are starting to get a full view.
Right.
And so that's been very exciting.
And I mean, we've known that stars have changed in brightness for a long time, as you said, or that's what, the discovery of mere variables, Cepheid stars, the fact that everything is kind of changing. But are there changes that are happening a lot more rapidly, the kinds of things that these space telescopes will discover that, as you said, daytime sharing, clouds, but just atmospheric variability? Like, are there changes that happen a lot more rapidly that these telescopes can pick up?
Yeah, so for the young stars in particular, we're finding that they're variable on everything from minute to multi-year timescales. And not only that, but their behaviors when looking at the light curves, we didn't realize this fully prior to looking with Kepler and specifically its K2 mission, but they fall into different categories actually. So some of them have repeating behaviors and some of them are just completely random. And some of them have interesting fading events that occur on like less than a day time scale. So you might, and they might be only like a few percent dips in brightness. Some of them are bigger. And these are things that are very easy to miss from the ground. If this particular dip happens over 5 hours and it happens during your daytime, you're never going to see it. You might see one the next night and then wonder if it's a problem in your data and not something, a real signal.
And I'm just sort of thinking about that process. Like, you've got this telescope, like say TESS, and it's staring. Like, I know that it takes a year to view one whole hemisphere, and how rapidly is it taking pictures of that region? Like, is it taking a very long exposure? Is it taking a bunch of short exposures, and then astronomers are stacking up the images and looking for brightnesses, changes in brightness?
Yeah. So there's a series of short exposures, and those are basically stacked on board, and then they are sent down. It used to be every 30 minutes, the entire field would be sent down.
Right.
Starting this July, it's going to, or actually, I guess it's already begun. It's every 10 minutes, with some more special stars actually get data every 2 minutes.
Wow. Okay.
Yeah.
And so that's the kind of thing that you would see a flare,
yes,
something else happening, as opposed to like a planetary transit goes on the order of hours.
Yeah.
Days.
Yeah. So they're very good for studying flares, for one thing.
Yeah. Yeah.
And also for both the young stars and what we're going to talk about even more weird behaviors.
Okay.
It's good at showing things that aren't necessarily repeating, because it's easier to pick up if something happens like kind of clock-like, which planetary transits do. But if they're just kind of, here's one, and then maybe 5 days later there's something else, and then maybe 2 days later or a week later, it shows you, is it a periodic behavior or not?
And I mean, are there some pictures starting to form above and beyond? Like, because I know, like with the Cepheid variables, it's a well-studied process, but these shorter-term behaviors, are you starting to build up a pretty good catalog of these kinds of events?
Yeah, absolutely. So it depends on what type of stars you're talking about. So for the young stars, the ones that are, when I talk about young, I mean things that are less than about 5 million years old. Many of those still have the material that they formed from circling around it in the form of a protoplanetary disk.
Mm-hmm.
That's dust and gas. So some of the variability comes from structures in the inner part of the disk occulting the star, kind of like a planet would transit a planet, only we're talking about much bigger structures. Then we have a gas falling onto the star and basically crashing onto its surface. And that creates bursts of brightness.
Wow.
Every time one of these so-called accretion events occurs, you see a big increase in brightness. Sometimes the star literally doubles in brightness. I mean, these are the type of events, when I say like crazy, weird young stars, that you would never see from the sun. The sun is basically constant day in and day out. And so the star could go down in brightness too if something blocks it.
I remember there was like one system, I think it was seen in infrared, but the star was giving off flares, and then astronomers were able to watch the flare, and then they were able to watch the reflection or the absorption and re-emission of the flare off of the disk, and they're able to use that to calculate the size of the planetary
Yes.
disk. And so really, I can just imagine, if you can see the brightness of the star and the regions around it, you can really start to tease out a lot of really interesting behavior that's going on with the star.
Yeah, it's really exciting. It is very complex, but it's basically our only way to map out what is going on in the inner astronomical unit or so around stars, because we don't have imaging technology to take pictures of those regions. It simply requires too high a resolution.
2026. Everything changes.
Yeah. We'll see. We need the 30-meter telescopes with interferometers, essentially.
So then let's talk about some of the more interesting, more exotic, the SETI-based things that you might be looking for as well.
Right. So the interesting kind of cross-section of what I do with young stars and SETI comes in searching for weird behavior. And in some years ago in the Kepler data set, this one particular star was identified as having unexpected brightness dips. And they looked similar to the young star behaviors in that there could have been something around this star occulting it, and it was not a repeated behavior. I mean, there were many events, but they were not exactly a certain number of days or weeks apart. But the thing that stood out, and this is now known as Voyager's star, is that astronomers could not detect any dusty material around this star, and there was no evidence that it was young, like the other objects that we had studied previously. So usually when we see something very chaotic or it has fading events or sudden brightening events, we can confirm that it's young via a variety of other types of observations, spectroscopy, infrared, photometry.
And so you had with Voyager star, I remember there was you had this fairly main sequence age star, and yet it was having these dips of brightness, the kinds of things that you would see, gas and dust, planets being smashed around it and that kind of thing. And it was weird. And that led people to say, what if it's an alien megastructure? Yes.
And then the media kind of ran away with that.
Not us. We held firm with just a purely, understandable. I believe, if I recall correctly, we just said it's dust. It's almost surely dust.
Yeah.
Can't be aliens. It's not. I don't think that we gave Dr. Kimberly Cartier, one of our co-hosts at the time, and one of the people who worked on the planet, on the star, a hard time. I don't think so. Maybe we did.
Yeah. So I think most people do believe now it's dust because dust has a certain signature when you are able to measure the brightness of the star in different filters. Dust occultation events tend to look more deeper when you look at red wavelengths, and the later behavior when follow-up observations were taken of Voyager star did seem to confirm this.
Right.
But of course, the idea was planted that, well, could there be other stars out there that actually have alien megastructures, and could we detect them? Now, the challenge with Kepler is that it looked during its main mission at around 200,000 stars. And that sounds like a lot, but it's really not too many if you consider, what the probability is of having an advanced civilization somewhere in our galaxy that could build giant structures around their star.
It's somewhere between 0 and 100%. It's in that range, I think.
Yeah. So if you take 200 stars, how many of them would have a very advanced civilization? You can take a guess at that. But really what we want is a larger sample. And Kepler wasn't able to provide that because its so-called full frame images, where it took data on the whole field, did not get downloaded to Earth very often.
So what would a megastructure look like?
Right. So what actually is a megastructure? People are familiar with this concept of a Dyson sphere. They're thought to maybe be a series of panels or basically any kind of structure. Could be loops going around the star or a full sphere. Something that a civilization would build to possibly harvest energy for themselves if they have a need for more energy than they could produce on their own planet. And the idea behind searching for them would be that those structures would then be in orbit around the star, and if they're not perfectly uniform, then as they occult the central star, you get interesting effects in the stellar brightness. Hopefully periodic with time, you get big dips that are unlike something caused by a stellar companion, a planet, or one of these young stars with disks.
As it's under construction. Once it's completed, then you have to switch to infrared, I think.
Yes, possibly. If it covers the entire star, you're out of luck detecting it.
Right.
So
we would see their Death Star in construction. But how would you be able to like really like what would be the signal that you would be looking for in the data to tell you that this is something that is artificial? What makes it different from just a planet passing in front or a blob of dust?
Yeah, so my group had a student playing around with this summer, in preparation for actually searching through the TESS data set, which is much, much larger than what Kepler had available. So we're going to actually look through probably 50 million stars or so, with data taken every 30 minutes for a month at a time, looking for dips of any type. Now, one can create models of what a stellar companion would do, an eclipsing binary, and that is a pretty well-known shape. It's usually a V shape, or a transiting planet would be a U shape, usually not a particular deep dip. So those kind of things we would immediately not think was a megastructure. What we're more interested in is shapes that cannot be explained by these known phenomena.
And when you say shapes, you mean like shape of the light curve?
Yes,
right.
Excuse me. Right. So we had a student imagining, what if not a megastructure is not only designed to harvest energy, but to tell us that they're there.
Right.
Maybe a megastructure, for example, if we built one, might consist of some language. Like, could you build a megastructure with the letters of your name?
I couldn't, but theoretically. So I know that, like, I remember, I feel like we did a story about this like a long time ago on Universe Today. And one of the proposed ideas would be like a triangle. Like if you had a triangle in space that was like a solar sail that was, it could be very lightweight, fairly easy to make.
Yeah.
And it would give off just an absolutely unquestionable signal that there was something really weird orbiting this planet. Very different from a planet, very different, or orbiting this star, very different from a planet, very different from a cloud of dust, a triangle or a star or, or a hexagon or something weird, right?
Yep. Yeah. So we have software in place where you can take any sort of megastructure shape and then model what the expected light curve,
right,
as observed with the telescope, would be. Now, the trick is, if we find something odd in the data set, can we go the other direction and go backwards and figure out what would be the shape of a particular megastructure?
Can you?
It depends on the complexity of the light curve. So, for example, I believe there were some studies of Voyager star where they were able to somewhat successfully model the brightness dips as a series of comets with tails.
Right.
So, but you do have to kind of make an educated guess first. I mean, I think if it's a really distinctive shape and then it repeats exactly, it's easier to do than something more complex and that might be changing over time.
What would it take to do a comprehensive survey for a significant portion of the universe, the Gaia mission of megastructure searches? What would that look like, do you think?
Well, that's a good question. I think
Gaia instead of searching for I guess what I'm wondering is, do you need something as sensitive as TESS? Or could you use, or I guess Kepler? I mean, Kepler was a lot more sensitive than TESS.
Yeah.
TESS is a lot less sensitive. But you're looking for something that's very obvious. So I'm not what would be the right profile of a mission to sort of really find those aliens?
Yeah, well, I think you still want good precision because that enables you to go deep into the galaxy. You want to be able to, so you don't need high precision on the bright stars, which is what TESS is doing. But the better you can do on the faint stars means the farther away and the larger the volume you can cover.
Right.
So we're going to look at 50 million or so stars, but ultimately, could we do a factor of 10, 100 times more stars if we had a bigger telescope? Possibly, yes. So if we had, Kepler with a bigger field of view, that would help. It all depends, of course, on the frequency and of advanced civilizations. And so if there's no one out there in our galaxy,
Right.
we're not going to find
Right.
anything.
And specifically, I mean, you're looking at the megastructures. Could there be a galactic version of this as well? Like, I know if you say you have a Type 2 civilization that has almost enclosed their star, a Type 3 civilization may have may have built a megastructure around some portion of their galaxy. Would you be able to detect that, or would things just be unfolding too slowly, do you think?
Yeah, I guess, would it completely block out the entire galaxy? I guess the whole premise of detecting things by doing time series photometry is that something has to be rotating around a light source on your time scale of interest.
Right.
So it seems unlikely to me that if you built something on a galactic scale that it would change on a month time scale.
Right.
Whereas certainly you can have structures in orbit around a star on much less than a month.
So when does the search begin, or have you already started the 50 million star search?
We're getting going actually right now. So the data has come down. That's 50 million number is the first 2 years of the TESS mission. We'll be adding more to that for the extended mission. But of course, I can't tell you whether we found anything yet, not because I have any secrets, but because the data processing takes a while. And there are analysis challenges with the light curves. There are systematic effects. And in particular with TESS, there are scattered light. There's scattered light infiltrating a lot of the images. And that causes strange effects in the light curve. So we are in the process of learning first what is an artificial effect in our data caused by basically Earth light first. And we have to remove that or mitigate it before we can going to be running some basically artificial intelligence methods, machine learning, because it's such a large data set, to look for anomalous behaviors among this giant data set.
Well,
and,
it's
absolutely
absolutely fascinating. If people want to watch the progress and find out the results, where should they go?
Well, as soon as we find anything interesting, we're going to be publishing in the literature. But if there's something very exciting, I'm sure the SETI Institute will put out a press release. We don't currently have like a group website. And so there isn't necessarily one go-to place for the project. But I can assure you that if we find something that even smells a little bit like an alien megastructure, it would probably be in the news.
Yeah. We've seen how this plays out already with Voyager Star and with Oumuamua and others. So yeah, we're ready. Yes. We're ready to be hopeful, optimistic that it's aliens.
And if not, our real goal is to put an upper limit on the percentage of stars with megastructures around them in our galaxy.
Fantastic. Well, thank you so much for joining us on the show today. Really appreciate it, and good luck. But don't find the bad aliens, or maybe you should.
I promise not to do that.
Yeah. All right. Okay. Great. Thanks. All right.
Okay.
Take care.
Thank you.
All right. Let's move on to the news portion of the week. Chris, you're on my screen. What have you got for us?
Can I just say a galactic superstructure just sounds unwieldy to me.
Unwieldy? Like you don't think that that's a thing that should exist?
It may be just my very small brain just trying to comprehend a
machine.
So
we've already begun the Dyson sphere, The Dyson
Yeah.
swarm around the Earth. Like every space telescope, every satellite that we put into space that is harvesting energy from the sun and blocking that light that would have gone out into the universe is part of our forthcoming Dyson swarm, right? And so eventually we will have just harvested all of it. Like, it won't just be like, let's just build a Dyson swarm. It'll just be like, oh, what do you know? We finished building a Dyson swarm. We now are harvesting all the sunlight. And then that'll happen for every single star in the entire galaxy. So it'll just, it's like your city. The city you live in, just, it's not like they overnight just paved the entire island of Manhattan. They did it bit by bit, building by building, until it was all done. So I think that's how it would go. It'd be like, we need more stars. Let's cover them with more Dyson swarms, until they might have a different name for it. But yeah. There's actually, I was going to bring this up with her, but actually there's been a couple of surveys that have been done in the infrared spectrum that have been pretty comprehensive, and they've looked for a very specific infrared signature that you would get from either a Dyson swarm or an entire galaxy that has been Dyson swarmed, and they haven't found any. So,
Okay. Yeah. I just have the image in my head of a giant Dyson sort of.
No, just 400 billion Dyson. The far more reasonable answer of 400 billion Dyson swarms. Come on, not one big one, 400 billion or a trillion if you're talking about Andromeda. What have you got for us this week?
Yeah. So speaking of galaxies, so how you actually build galaxies is a very fascinating and large subject. And the violent process of mergers is an essential element in our story of how galaxies ultimately came to be in the universe. So massive galaxies like the Milky Way and Andromeda are both believed to have survived this chaotic era of galaxy formation billions of years ago, through this hierarchical buildup of smaller galaxies forming larger ones. And however, although the heyday of this galaxy mergers in the early universe has come and gone, galaxies do still merge from time to time in our local corner of the universe. And recently, an international team of astronomers as part of the Hubble HIPEC survey, which is this survey aiming at studying galaxies in extreme environments, released this beautiful collection of images taken from Hubble, capturing these cosmic car wrecks with great detail. And I must admit, part of me choosing this article was just so we could look at these pretty pictures together.
Yeah, I'm going to figure out a clever way to be able to show the pretty pictures off, because you're exactly right. They're pretty amazing, but let me see if I can, do this. That didn't work. Let me see, because I have let me try one other thing here. Because you're exactly right. You put me on the spot. Let me see. Okay. I'm going to share. Did that work? Nope, that didn't work. We just get Zoom.
Ooh.
Nope, that didn't work.
Well, I saw the images.
Yeah, you've seen the images.
Yeah, I saw them too, actually.
You
Yeah, I
guys
saw
did,
them.
yeah, but the audience did. In fact,
Oh,
they still don't, which is so weird.
And I was just wondering, what if the stars in the galaxy are the swarm?
Yeah, so that's really weird. Huh, okay, hold on. So now it's just like the whole chat. All right, let me do something here. Turn that off, turn that on. Nope, okay. Hold on. That was a horrible mistake. Look what you did. Oh my God. Did that work? Come on. All right, let me try something else now. All right, well, back to me. Weird. Okay, hold on. So I'll grab a window, capture, zoom. Okay. Show the zoom. Nope, it's gone. Oh my God, this is completely... Did that fix it? Nope. Huh. We have totally destroyed Zoom. Okay, I have another plan, but I don't like it. Okay, let me try one other thing. Nope, has not come back. I'll try hiding Slack? No, it just makes the screen completely dead. Okay. All right. So we've learned a valuable life lesson. Do not try to screen share in Zoom when you're using OBS, and it completely destroys it. Okay. Let me try one more thing. So let's see. There's the Slack chat. I'm going to add a browser. No, I'm going to a display. And I'm going to go with, is it that one? No, not that one. That one. Okay. So now I've got you on the screen. And then I should be able to put the screen in front of you now. All right. So that worked. Talk about the sausage getting made. All right. Okay, one more. Turn that off. What the? Okay. Okay, now I've got it figured out.
So they can see them now? Is it?
Not quite, not quite. I'll put it on the screen, though. I can definitely put it on the screen like that. So now people can see it. There, we did it. We did all that work. And if you want to see, you guys want to see what it looks like, you should be able to see it. Except when I click on that.
Oh.
Hold on. There. There. On your face.
Perfect.
Yeah, exactly. And I'll just keep fixing it while you're talking. What are we looking at, Chris?
Okay, so what you're all seeing are these 6 images from the HIPEC survey about these merging galaxies, and these 6 pictures that were used as they released to the public. And so of course these are great galaxies to look at, but they also tell you some interesting things about galaxies as well. So first is that the galaxies are almost entirely empty space. And so on their first approach, as these galaxies are merging, they're kind of like phasing through one another. And that's, so then their mutual gravitational attraction sort of draws them back to each other. And so over time, they sort of form these like lobe structures that kind of look like butterfly wings. And you can see one of the examples, it's an NGC 3690, which in the graphic you're showing, it's in the bottom, well, I guess my left corner.
Yeah.
About the example, and this collision is about 700 million years old. I think my personal favorite is a NGC 6052, which is the bottom center, because it shows a disk and another disk galaxy that's kind of like cartwheeling into the other one.
Right. One is just like smashing into it sideways.
Yeah, it's like slicing it in half.
Yeah. Like throwing stars. That's amazing.
But also another interesting feature of these mergers is not only are so when the galaxies go through each other, the gas in each of the systems are smashing into one another. So this is what we mean when we say the gas is being shocked. And so it's this rapid concentration of gas at these high densities during these intense collisions that you create the perfect conditions for this unbridled phase of star formation.
Right.
And this is why all these images they're kind of peppered with these bright blue knots of newborn stars. And so there's a lot of interesting physics going on in these images that I'm sure we'll be parsing through more so in the coming years.
So, I mean, it's interesting, like Hubble released just these 6. Was this just like their 6 recent favorites? Are any of these famous? Like, have we seen these before, or are these all new? I mean, the problem that I always have with the Hubble Space Telescope is that the power of the telescope is so much that, you know, you'll see galaxies like I don't know, Andromeda, or you'll see M33 or things like that. But then or the Cigar Galaxy or whatever, very famous galaxies. And then you'll see these galaxies with this level of resolution and think, oh, these are just tiny, galaxies that for our telescopes would look, for a regular telescope would just look like a tiny little smudge if you could even find it. But for Hubble, they can show all this detail. I mean, this one's crazy. All of the one, as you said, the one that's sort of coming in sideways, and you can see the knots of star formation as it's piling up. What is the outcome of these galactic mergers?
Yeah, that's a great question, because I think it serves as a nice segue about what we can expect about the Milky Way's future, because these merging galaxies that you're seeing here is very similar to what we should expect with the Milky Way and Andromeda in 4 to 5 billion years. And so eventually, so the end result of these mergers, exactly what we expect to be the end result with the Milky Way after its merger with Andromeda, is this very long process of slowly sort of conglomerating into a single massive elliptical galaxy. And in the case of the Milky Way and Andromeda, the name I think that's floating around is Milkomeda.
Milkdromeda.
Milkdromeda.
Yeah. Like I've got to put my foot down here. I feel like maybe 10 years, 15 years ago, because people were starting to already float like Milkomedia, and that just can't stand. So I have really put like a full court press to try and push the idea of Milkdromeda. So is that the official name? No. Is it vastly superior to Milkomedia? Yeah, come on. So please.
We have billions of years to make up our mind about it.
It's true. We do. Yeah. We got a lot of time on our hands to sort this out. So we'll wait for a really good name to come along. But it's interesting. Like in the end, the galaxy will be just one of those big balls, one of those big elliptical galaxies, right?
Exactly. Yeah.
Yeah, and then not that interesting to look at. And then it'll die over long periods of time, just turn redder and redder and sadder and sadder. Awesome. Thanks, Chris. All right, Carolyn, what have you got for us?
Yes. Well, I went to the American Astronomical Society meeting, like probably everybody else did the last 2 weeks. And
weren't we there a year ago together in Hawaii?
I didn't get to go to Hawaii, but
that's
right. A
right.
couple years ago. Yeah. But as you know, they're all being held virtually, so we basically sit on our little heinies in front of the computer for 8 to 10 hours a day, going to paper sessions. And aside from the press conferences, I actually got out to some of the other sessions. And one of them that I got to was this thing on the history of astronomy. They have several sessions throughout the week, and one of them was about the Voyager mission. So everybody knows the Voyager mission went out to the outer planets. So Voyager 1 went to Jupiter and Saturn, and Voyager 2 went to Jupiter, Saturn, Uranus, and Neptune. And then they're leaving the solar system. They left the scene, sent back all this data. So they're on the Voyager interstellar mission now. They're outside of the solar heliosphere, and they'll be transiting the Oort cloud for a while. And they're currently transmitting intermittent messages back and forth that convey information about the conditions that they're encountering. Kind of a, hi, we're here. Here's what it looks like right now. And they'll do that till the transmitters stop or they run out of power, at some point. So that's not the whole story. The story was, since they're going to interstellar space, there's a chance that, however small, they might get found by intelligent life. So instead of us looking out at the stars at Voyager or whatever, they were sending this message out there. And if it gets found, then they're carrying this message that's kind of like a message in a bottle. And the scientists on the Voyager teams, led by the late Dr. Carl Sagan, created what they call the Voyager Gold Record, which is encoded with the sounds and images of Earth. So people talking and babies crying and whales singing, and there's pictures, and it's really quite evocative. The records are encased. They're placed on the side of each spacecraft, and they're encased in these protective covers that have information about how to play the records, what location of Earth is, what humans look like. There's some rudimentary science information.
Yeah.
Oh yeah, there's a whole side story about that, And the messages are basically designed to let other life forms in the universe know that we once existed. So the big question is, we know they're going out there, and a grad student named Nick Oberg, who's going to school, I think in Denmark, I can't remember now. He presented a paper at the history session that about what could happen to these two spacecraft. And essentially he asked, what will happen to the Voyagers, and will their gold record survive? Will our message get out there? And the short answer is, of course, the spacecraft are likely to survive unless they whack into something that we didn't know about, but the records may not. So he came up with a scenario. In about 20,000 years, he says, the Voyagers will exit the Oort cloud. They'll be totally out of the solar system, any vestige of the solar system, and they'll be orbiting the center of the galaxy, just like the Earth, like the sun does. So they'll be at about the distance of the sun. So Voyager 1, if you think about it, here's the galaxy. Voyager 1 is headed out this way, sort of out off the plane of the galaxy, and Voyager 2 is going to more or less stay inside the plane of the galaxy. They'll orbit around like the sun and stars do. They're not going to just be in empty space. They're going to be orbiting through these molecular clouds. They'll get bombarded by microparticles. They'll get hit with cosmic rays, all this stuff. So if, depending on where they are, Voyager 1 sort of is going to be in a less stellar dense area than Voyager 2, but they're going to go through these clouds and they could be bombarded by these microparticles. And so the very worst damage you're going to see is the cover will be completely etched clean. You won't be able to tell what the instructions are. So our aliens are going to get this and go, what the hell is this, Voyager 2 might not go through quite so much, might not have as much etching, but if it does go through, if either one of these go through a lot of clouds, they could get completely etched away and the records could be completely destroyed. Right. So our message in a bottle doesn't happen.
I'd heard that when they originally designed them, they were expecting that they would last 1 billion years.
Yeah,
that was the plan.
And in fact, that's the point that Nick started with, is at least 1 billion years, depending on what they go through. And again, when we launch them, there are these clouds here, but then in 1 million years or 5 million or 1 billion years, those clouds could be gone, could be replaced by others, just depending on where they're going, what their gravitational perturbations are, what they're affected by. Well, so Nick extrapolated a little farther on into the far future, and he said, well, what's going to happen if they survive the microparticle cleansing? What's the far future going to look like? And that brings me to the Milky Way and Andromeda, right? We just got through talking about this. They'd witnessed the creation of Milkdromeda. So if they still existed, they could also be these kind of silent witnesses to the interactions of our galaxy with the large and small Magellanic clouds. Now, the other thing is, if they do get through these, they probably aren't going to be destroyed by the collisions, but as a result of the shock waves and the other events that go along with galaxy mergers, the spacecraft could get tossed off into different orbits or maybe even completely out to intergalactic space. But the story doesn't end there. They could be traveling through the local group, and in a few billions of years, the local group merges, and billions of years from now, or maybe even like 100,000 trillion years, the Voyagers could end up orbiting in this very old, massive elliptical galaxy. And they did this by extrapolating what's going to happen astrophysically, as well as what's going to happen as these spacecraft go out into space. Now, of course, if they whack into some rock between here and wherever, all bets are off. And we still don't know what happens with our messages. If they survive, maybe somebody finds them, they get to play the messages and they know about it.
They've only got about 10 years left before they completely run out of power. And then it's sort of asking
10 to 15,
it's like, what does a rock perceive as it sits on the ground for 3 billion years? Right. Yeah. And of course, the chances of anybody finding them are incredibly remote, and merging with them and returning to Earth and attacking
becoming
us.
Voyager.
Is obviously the inevitable outcome. Very cool.
I don't think they get really much closer than about 40 light years to any star, unless something happens to them to send them off in another direction. So,
and
that's
like
a good point.
Long periods of time. Like I know. They're already close to 40 light years. No, they get like within a light year of some stars along.
But they're saying of most stars, but there's a few stars they do get fairly close, but not.
There's
probably,
a few that there are, over the next, say,
they're
50,000.
like the average distance.
Over the next 50,000 years, they will get a couple of times close-ish to various stars, but still, space is big. You won't believe.
I want to ask one thing about that galaxy circling thing that you want to build. What's going to be the effect of dark matter on that?
Well, the same. You're just gonna surround each one of your stars with a Dyson swarm. So the the average mass of dark matter in the solar system is about the mass of a small asteroid, like a Bennu. So it actually doesn't have that much of an impact on the galaxy. It's on each individual star
out
system.
to the galaxy.
Yeah. It has an effect across the entire galaxy, but because solar systems are actually so small compared to the size of the entire galaxy, that amount of dark matter is distributed quite nicely across vast volumes of space, and so it wouldn't have any effect on a real local level. So don't worry.
I'm just trying to think of all the details.
Glad somebody is. All right, Pam, what have you got for us? What should we be watching out for?
I thought we would have to be worried about Voyager sending people here. We're going to be long gone.
Yeah.
So if you're an astronomer and you remember the amazing events from last month, don't fret, because there is another big conjunction coming soon. But let me talk a little bit about a couple things still happening. Mars is still bright and high in the sky, and it's kind of southish. Vesta, I guess, is going to be visible with binoculars in the tail of Leo. They say it's a 6.3 magnitude, and you're gonna have to wait for it to come up in the east, though, and it's going to get easier and easier as you go through February and March. Full wolf moon on the 28th, and they're saying it's near the Beehive cluster, M44. And, I always like to talk about, a big bright object like the moon is a good way to find other things that are dimmer. But, full moon might be too bright. But these will both be rising in the east.
Yeah, I don't like to use the moon to find anything in astronomy.
If it's small, it works okay.
Yeah, maybe. Yeah. That bright star near the moon is Jupiter. That kind of thing. Sure. Yeah.
Right. Yeah. And also Venus and Pluto are in conjunction. We'll see them in the early evening in the west, I believe it is. You are going to need help to see Pluto, of course. And I have a really big list, so I'll just go pop through a couple of these here, because the big conjunction is going to be on February the 10th, and that is going to be Mercury, Venus, Saturn,
That's
Jupiter,
cool.
and the moon. Well, I'm not sure, because they're very close to the sun right now, so are we going to be able to see it? I'm thinking maybe in the in the east, right before sunrise, right? And I'm thinking maybe it's going to be better with some kind of virtual telescope, but that's always fun to do too.
Yeah.
I think looking for yourself is great, but looking with a big telescope that somebody's running somewhere else is okay too.
I can't see Mercury, so I just
I
just have to take your word for it that Mercury exists.
I feel so bad for you every time.
Yeah. I have my doubts.
All right, so February 11th is the new moon, Venus and Jupiter in conjunction. That's going to be low in the east before sunrise. I guess, again, I don't know. They're really close. They're so close to the sun. They're going to be transiting between the evening and then the morning between now and like the end of February. We've got Mercury and Venus in the conjunction on the 12th. The moon is 1 day old, so that's going to be a good thing to see in the night sky. A nice little moon, Mercury and Venus, that kind of stuff. And let me just I'm going to go ahead and talk about the first quarter moon on the 19th. And what I'll do is kind of like usual, I'll put this list in the comments at the end, because
Awesome.
I know we're really, really close to our time, and I want to be considerate of our viewers.
So yeah, the quarter moon is my favorite. That's
Yeah?
I think, because that's the one where you get the shadows across the surface of the moon, the one where you can really see the features on the surface of the moon. Once you go to full moon, there's nothing to see. New moon, obviously, nothing to see. But that quarter moon, you've got the sun coming in from the side. You got those nice long quarters, long craters, nice long shadows. That's the best time to look at the moon.
Yeah, I think anywhere between like the first day and almost full moon, you've got the Terminator, and it's
That's
gonna
true, yeah.
show you. And I've seen pictures of where people have taken night after night, and it changes, and it's amazing. And just really, really good, crisp pictures of that. They're just wonderful to see. So.
Any meteor showers happening this month?
I looked and I didn't see anything between now and like the end of February. So I don't know about March yet. We'll have to look again.
Right. And any eclipses coming up?
There are 2 for the year, but they're gonna. No, I guess it's more than 2. But where are my notes?
But they're later on.
Then later on.
Yeah. Okay. All right. Well, you'll
Nothing. Anytime
you'll tell us
soon.
about it. Yeah, as we get
Oh
closer.
yeah. Oh yeah. I'll
Awesome.
be back.
All right. Well, you know what? You're on my screen, Pam. So if people want to find out more, what are you working on? Where can they find out more? Let's see your book.
Sure. Yeah. We've also got. Let's see if I can figure out how to do my book now. I think it's
Hold
here.
it up. Oh man, you're gonna
Sorry.
tempt it. All right, you're gonna try. We saw what happened to me. Don't be like me.
It'll work. There it is. 'Cause it
Awesome.
never shows up when I show it.
That did work. Yeah. Fantastic.
Yeah. And so, we've got our Friday night show now, and it's really fun because we have a guest a lot of times. But when we don't have a guest, we have started a new series of citizen science. On Friday the 29th, we are going to be talking about Planet 4, which is a new project on Zooniverse. And this is going to be where you can find things on Mars. I think that's really, really cool. Jeff's doing a whole bunch of research on that.
That's really
and, yeah,
cool.
we want to find you on Facebook or on YouTube. We have a channel. Everyday Spacer is on the YouTube as a channel. And then on Facebook, Everyday Spacer is a page. So if you come there during the show, we do chat with you and answer your questions. And we really love to talk to all of our guests. And yeah, it's available afterwards all over the place. I'll go and share on a bunch of places on Facebook for the replay.
Perfect. Wonderful.
Yeah, fun.
All right, Chris. What are you working on? Where can people find out more?
Still very much inside right now, so not too much exciting. But if you still want to follow me, you can follow me on Twitter at @TheRealCCar.
And are you working on anything interesting?
Homework.
Right on. Okay. Carolyn.
You can find me at thespacewriter.com, and right now I'm finishing off going to work on a full dome show about exoplanets, and mostly staying inside and quarantining until I get my shot.
Me too. Waiting for that. Waiting for that shot. I can't wait.
Yeah.
All right. I'm going to put all of us back on the screen. There we go. All right. Well, hey, thank you everybody for joining us today. Even the technical problem, I will sort that out. I'll figure that out for next week. Thank you to all of our good friends of the Weekly Space Hangout crew, especially Nancy Graziano for keeping us all organized. We really appreciate it. All the mods, everybody watching both on YouTube and on Twitch. And, of course, to our special guest, Dr. Marie Cody. That was great. And hopefully we'll find the aliens. All right, thanks, everybody. And we will see all of you next week.
Good night.
All right. Press the button.
Live is always fun, isn't it?